Kia ora koutou, this video is about parallel wires. Looking at parallel wires, putting two wires close together going in the same direction, it's a really good example of how we can use our right-hand rules to figure out things about the magnetic field and the force between the wires. It's also a context that has been used in the exam before, so it's a good one to look at. So say we've got this pair of blue wires here, and they're next to each other. You can see they're parallel and they've got current running through them, and the current is in the same direction. They've both got current going upwards. So two things happen here. One is that the current going through these wires creates a magnetic field around the wires. The second thing is that the magnetic field around the wires creates a force on each of the wires. So like the magnetic field from wire 1, we'll call it B1, causes a force on wire 2, and the magnetic field on wire 2, B2, causes a force on wire 1. So we're going to figure out the direction of these forces using our right-hand rules. So first thing we need to do is, for our wire 1, figure out the direction of the magnetic field around it. So we use our right-hand grip rule. Get our right hand, we put our thumb pointing upwards, because the current's upwards, and our fingers curl around, going around the wire. So that's how the direction of B1, the magnetic field around wire 1. You do the same thing for wire 2. Put our thumb upwards. We see that wire 2, the magnetic field goes in the same direction as wire 1 did, because the currents are both going upwards. So the magnetic fields go the same way around the wire. Alright, now if we look at this B1, this magnetic field around wire 1, let's look at where it overlaps or enters wire 2. So when this happens, because it's a magnetic field going through a current, then we're going to get some force. And remember, the equation that we looked at for that force is F equals BIL. So it depends on the strength of the magnetic field, the amount of current, and the distance we are between the wires, so the length of the wire in that magnetic field. Okay, so we use our right hand to figure out the direction of the force on wire 2 caused by the magnetic field of wire 1. First thing to do is, looking at this point here, which direction is the magnetic field going? It's going into the screen. So we put our fingers, first we uncurl our hand, make sure it's totally flat, put our fingers in the direction going into the screen. Now the current is going upwards, so we have our thumb going upwards, and then our palm should be pointing in the direction of this arrow F2 here. So the force on wire 2 from wire 1 is pushing to the left, pushing wire 2 towards wire 1. Now if we look at the force on wire 1 from wire 2, the magnetic field B2, when it enters the wire, it's going to be coming out of the screen. So we put right hand, put our fingers going out of the screen. Our thumb should be pointing up, because the current in I1 is going upwards. And our palm then should be facing to the right. So we see that the force on wire 1 from the magnetic field around wire 2 is also pushing wire 1 towards wire 2. So both of these forces caused by the magnetic fields around the wires make the wires push together. What about if we have parallel wires with the currents going in opposite directions? So see, the difference here is now that I2, instead of going upwards, is going downwards. So what's going to happen here? Well, again, we can look at the magnetic field direction around wire 1 using our right hand grip rule, putting our thumb up because the current's going up, and we see that the magnetic field is going around this way because that's the direction our fingers curl for wire 2. Now we put our thumb down and we see that the magnetic field is going in the opposite direction as for wire 1. That's the way our fingers curl. Okay, now let's look at the force on wire 2 caused by the magnetic field B1. Get our right hand, put it flat. We put our fingers going into the screen because the magnetic field is going into the screen at this point. We put our thumb down because the current I2 is going down. And we should see that our palm is pointing out to the right hand side. So F2, the force on wire 2 from wire 1 is going to the right. So we look at wire 1, this point here where the magnetic field intersects with wire 1. Now the magnetic field is going into the page, so we get our right hand, put our fingers into the page, put our thumb up because I1, the current is going up. And then we see that our palm is pointing outwards. So F1, the force on wire 1 from the magnetic field around wire 2 is pointing to the left. What we see is that when we have wires with currents going in opposite directions, they push apart from each other. So the forces from the magnetic fields around those wires push them away. Let's look at it from a different angle. So to make sense of this angle, we have to know how we can more easily draw the kind of 3D picture that we've got here. So remember that if we want to draw a magnetic field or a current coming out of the page, we can just do it with a whole bunch of dots. Because it's like an arrow, so if an arrowhead was coming towards you, you would just see the point of the arrow, so you would just see like dots. So this is like 25 arrows coming towards you. Over here, we've got some crosses. That's if we have a magnetic field or a current or a force or anything coming into the page. Because that's like seeing the back of the arrow as it flies away from you. You see the crossed over feathers at the back of the arrow. So what we have in this picture is like the view from the top of those two wires. So these circles with dots in them are showing the wires, and the little square dot in it is showing you that the current's coming out of the page. So we're looking down on two wires and they both have current coming towards us out of the page. Then we can look at how the magnetic field is more easily for those wires. We see that, right, we can use our right hand grip rule again. This time our thumb's coming towards us and our fingers wrap around. So we get this anti-clockwise circle of magnetic field around both of the wires. And we can see how this field joins up because the fields are going in the same direction. So that's another kind of way of looking at why the wires push together, why the force is pushing the wires together, because the magnetic fields are joining together. Versus if we look at the two wires with a view from above going in opposite direction, right, we can see that this wire on the left, because it has the cross in it, the current is going into the page, away from us, and we can see this wire, the current is coming out of the page towards us. So again, we can use our right hand grip rules. For this one over here, we put our thumb away from us, and so we see our fingers curl around in a clockwise direction. For the wire to the right, we see that we put our thumb out, and the magnetic field, our fingers curl around in an anti-clockwise direction. And then the magnetic fields interact quite differently. So we can see that the fields aren't joining up and adding together. They're kind of causing a repulsion effect, and that is why the current carrying wires are moving in opposite directions or feeling a force in opposite directions. So that's parallel wires, just an example of how you can use these grip rules and right hand rules to start getting kind of complicated, but seeing the effects on actual real world wires. So the parallel wire example is important because electrical engineers, obviously they're putting a lot of wires together, say when you're putting electricity wires in the streets or underground, even in homes, it can be important to think about the forces that those wires are going to have on each other and how to make sure you're putting all of the currents in the correct directions to make sure that the wires aren't going to be like pushing each other apart or sticking together.